Okay, so we want to now address the question of what produces a magnetic field. So what produces a B field? And the answer is going to be charged particles in motion or currents. So we can imagine that we have a charged particle of charge q naught, and it's moving with some velocity v that way. And we have a detector that measures the magnetic field, and we can do some experiments. So let's say that we try to measure the magnetic field here. Well, we'll end up finding that the magnetic field over here, let's just draw it with a pencil. Its direction over here is into the page. Okay. Let's say that we try to measure the magnetic field over here. We'll find that the magnetic field there is out of the page, and it has the same strength as it does over here. So let's say that the distance from here to there is the same as the distance from here to there. And if we move further away this way, say over here, the magnetic field will get weaker, and it's let's say the distance over here is twice as far. We'll find that the magnetic field has 1/4 the magnitude that it does here. Similarly over here, except the direction has changed, so we would make a smaller dot. And so what we start to realize is that the magnetic field sort of circles around the source of the magnetic field. And we can imagine doing this in great detail and coming up with an expression for the magnetic field. And we have some units. There's some constant, mu naught, there's a 4 and a pi, and the value of the charge q naught. And we have the velocity, makes a difference. If that goes to 0, the magnetic field disappears. We have a strange cross product in the field, just like we did in the magnetic force. And then the 1/r² expression that we saw for the electric field as well. So this is a very strange kind of expression. We want to get a better sense of what this means. So we were thinking of the charged particle moving that way, so the direction of the velocity is that way, and I wanted to first find the direction of the field here. So this quantity in here, this is a vector product, and so the magnetic field is given by a vector product. And these are two vectors. The velocity, we understand physically what that means. This quantity is a unit vector pointing to where we want to know the direction of the field. So if we want to know the field here, I have to point that way. So as usual, the right-hand rule requires that I consider the index finger for the first vector and the middle finger for the second vector in the vector product, and the thumb is the result. So I wanted to find the field here. I'm just trying to capture mathematically what I found experimentally, and this is the way it does that. So velocity that way, my index finger. The middle finger represents the r hat, the direction to where I want to know the field, and so I have to point that way, So velocity is this way. I have to point that way because I want the field over here to the right, and my thumb is pointing into the page, and that's why I have an X. And that's true of any location to the right because the velocity is that way, and my middle finger is pointing to the right, and so my thumb points into the page. Whereas on the left-hand side, the velocity is still pointing that way, and the middle finger now is pointing to the left, and so my thumb is pointing out of the page. Okay, so the magnetic field circles around the source of the magnetic field. But just like we did in the electric field case, we want to really think of continuous distributions of charges in motion or currents, and so we want to construct a version of this that allows for the existence of currents. And so let's consider the tiny little field, the infinitesimal magnetic field dB, produced by a tiny little charge in motion, dq, just like we considered the tiny little electric field dE produced by a tiny little bit of charge, dq. So this becomes, nothing else has changed except we replace the q with dq, and so we can think of this as ultimately as an integral, where we integrate over all the little pieces of charge. But it's better to think in terms of currents, so let's write this dB as mu naught over 4 pi. Now let's take advantage of the fact that V is dr over dt. So we can say, let's just write it in two steps. So we have dq, then we have d, say r over dt cross r hat, all of this over r squared. And so we can recognize that, I can, in a sense, move the dt over to here and think of these as ratios, right? Think of the derivative as a ratio. And so I can write this as mu naught over 4 pi dq over dt times dr cross r hat over r squared, and then recognize that this quantity here is what we normally think of as current. So we define I current, let's write it out. Current is just the time rate change of the charge, and so we get that the infinitesimally small magnetic field produced by some current looks like that. Okay, and so overall this gets us to the magnetic field produced by current, where we have a constant, but we have to integrate over all of the current, like that. It's a very tricky and, in fact, complicated mathematical expression to find the magnetic field, and this is called the Biot-Savart Law.